some papers written. So the universe, we know, come out from the Big Bang. The very early moment at the beginning of its life is deep into quantum gravity regime. So that's where quantum gravity should play a role. And a lot of colleagues have applied loop quantum gravity to describe what happens there. It seems to be working, and to see if one can predict effects of what happened there that can be tested in the cosmic background radiation. It's possible. People are working, measurements are getting more precise. I hope they will convert to something useful, but for the moment, there's nothing. That's one. The second one is black holes. I'm working on black holes. Loop quantum gravity is consistent very much with the idea that a black hole evaporates. That's Hawking great realization. Black holes evaporate. They become smaller, smaller, smaller. And then at the end, they don't just disappear, pop out of existence, but there's a remnant, which is a white hole. So there's a quantum gravity transition, a jump, the famous jump of quantum mechanics, from a black hole to a white hole, with a little throat but a huge inside. And then this white hole slowly, the things come out, so the information slowly come out, lives for a very long time. And this is a scenario, it's a possibility. It might have astrophysical consequences. These are being explored, various groups, including in London, the people I'm working with. Is one of these possibilities which I'm particularly attracted to, which is that these little things that float around in the universe, these black hole remnants, which are white holes, are actually dark matter. That's what, or a component of dark matter. If so, it might be that we have already observed something, we just haven't recognized it.
Right.
Okay?
Dark matter being another great puzzle of modern
dark
physics.
matter it's a big puzzle, and that's the opposite of the quantum gravity puzzle, because it's not a puzzle in our understanding; it's a puzzle in what we see. So we see. You look at the universe around us, and we see galaxies, stars, clouds of hydrogen, all sorts of stuff, and then there is this stuff out there. We're not even sure it's stuff. I mean, there's something that produces effect out there. We see the gravitational effect of these things, and we have quite convincing evidence that it's not usual matter. It's not just atoms or molecules or protons or neutrinos or photons. It's something else. And it's a lot. It's quite as much normal matter and dark matter, even more dark matter than. And nobody knows what it is. So it's fantastic. It's just, people who say that we're close to the end of physics and close to the theory of everything. Come on, guys. We don't even know what we see around us. So dark matter is really an open question. We have a lot of possible explanations, but too many and non-confirmed, non-really credible. I like the black hole ones because it does not rely on any new assumption. You can say, dark matter is some new kind of particle we haven't seen yet. While if it is black holes, it's just general relativity and quantum mechanics.
Right.
So something we know exists. But I don't know. It's an open question.
It's funny you said it's a mystery, we don't know, and that's fantastic. And that that's not always the case in a lot of professions where the lack of knowledge about something is something you're excited about. Are you glad that physics is nowhere near being complete?
Oh, infinitely so, of course. Of course. Yeah. Otherwise, it would be boring, right? If we imagine what a disaster if we got somebody wrote, okay, I got it. Everything is the final equation of everything.
But that's what you're going for.
No.
No?
No. Zero.
Is it quantum gravity not sort of that grand unifying theory?
No, it's a step on the way.
Okay.
It's just figuring out what are the quantum properties of space and time. I mean, then there's so much more to figure out. I'm not working for a theory of everything. I'm working just for a next step in understanding what's around.
So what would be beyond quantum gravity in our understanding, or once we've figured out the quantum nature of space-time, does that open up new questions or help us answer old ones?
You're referring to fundamental physics, right? Because of course there are plenty of questions which are not fundamental physics, like what is consciousness, or how a thunderstorm really works, which haven't been figured out yet. But in fundamental physics, suppose loop quantum gravity is confirmed, okay, I with a colleague, Marius Christodoulou, we have an experiment which we proposed, which might even be doable in 10 years or so, which would actually test the discreteness of time predicted by loop quantum gravity. So suppose this can be done, okay? And bingo, the right numbers because loop quantum gravity predicts that space is discrete, right? It's granular, nothing continuous, it's really granular. Like light is made by photons, space is made this grain of space, but also time I expect it has this granularity. And we have an idea of perhaps with some slight advance in technology, not excessive, could be tested. Now, suppose this come out right, okay? Bingo. Loop quantum gravity is correct. Perfect. The right numbers are there. Now what? Well, now we still have a universe described by a funny standard model where the weak interaction and the strong interactions are completely separated, described by similar theories, but not really unified in any way. Gravity described by still another theory. 19 parameters of the standard model, with who chose them, why 3 generations, why? We have, suppose with quantum gravity, we figure out the Big Bang. And what seems likely is that it was not initial explosion, was a bounce. It's an idea, not just in loop quantum gravity, the idea studied by various people.
That our universe is the result of a previous one collapsing
so there
and
was
expanding again?
some universe that was collapsing in some sense under its own weight. It gets to the sort of maximal compression where quantum gravity comes in, it bounces, and what we see as a Big Bang is this bounce. I think it's a reasonable hypothesis. It seems to be more reasonable than the Big Bang, but we don't know. Suppose we figure this out. Have we solved everything? No, of course. I mean, what was the collapsing universe coming from? I mean, what was there?
Yeah.
I mean, it's all open. It seems today so impossibly difficult to figure out what was in the collapsing universe. But, at the time of my grandfather, it seemed impossible to discover what was the chemical composition of Jupiter.
Yeah.
I mean, it was considered unsolvable problem. I mean, now we know in Jupiter everything. Even, there were ants there we would have seen there. So science finds new problems and grows at all levels. And know if there are mysteries is not a reason of sadness, it's a reason of joy because there are new things to discover. It's a beauty of understanding.
You're still like Isaac Newton playing with pebbles on the vast sea of what we don't know?
Absolutely.
Yeah.
And regarding this, general idea of working in a field where you maybe don't yet have evidence for or against it, it just reminds me of something you write about in your book, The 7 Brief Lessons. When you're talking about Einstein's theory, you write about how a lot of times something very important is kind of considered useless at the time when it's developed. One example you gave is that Riemann's work that was generalizing Gauss's explanations was considered useless at the time, but it was then a fundamental piece of Einstein's theory. So it seems that this is very crucial to work on things where we don't actually know exactly what the application will be or exactly how long it will be. But I'm wondering if you think that physicists need to find in general some kind of a balance between working on problems where we have an idea of the time horizon for the applications versus working on these problems where we don't really know where it will lead.
Yes, obviously there is a balance to be searched there. I think if you look at this from the main whole of perimeter institute, it seems hard to find balance. But if you look at it on a large scale, 99.9% of the money put into research worldwide is to practical applications. And the tendency is to go more toward practical application. And that's a disaster, I think, because of course we need practical application, right? We need people who study chemistry of material because we need a certain material for something, for healing people and replacing bones. I'm just defending. So applied science is great, but to concentrate resources toward applied science so much as is done today, I think it's a disaster. We need people who are who do the kind of pure science